Afternoon session. I'm sure all of you are familiar with the process by now. We are inviting questions through the Q&A channel. The chat is used for other functions and communicating between people, but it makes it much easier for questions to Roy through the Q&A channel, so please use that. We're not automatically offering live captions this afternoon because they were causing a few problems. However, if you need them, would you please put something in the chat and we will enable them from there. The recording's already begun, so it's my privilege this afternoon to introduce Roy Llewellyn. Roy approaches radio from a scientific and an engineering standpoint. He's the designer of EZNEC, and he's the author of many articles on radios and transceivers, their designs, and on baluns and antennas as well. And he has a rather intimidating bookcase behind him, so I'm sure many of those articles are enshrined in there. So please do submit questions through the Q&A, and Roy, it's over to you.
Thank you, Nicholas. Yeah, I apologize for the bookcase. It's kind of iconic. Everybody that does all the talking heads seem to have a bookcase behind them as an attempt to impress people, and that's not the intent here. The reason that I've got a bookcase behind me is that my office is an absolute disaster. You wouldn't believe the mess it is. And the bookcase is the only place where things are more or less lined up. And even though you can see they're kind of stacked up and leaning as it is. But anyway, that's the reason for the bookcase, not to impress anybody. But a great number of the books are electromagnetics and antennas, textbooks, a few mathematics and that kind of thing also, and I do refer to them fairly often. Well, let's see. The talk today is going to be about antenna modeling, but I'm going to really be talking a lot about EZNEC, which is the product that I first introduced in 1990. Well, actually 1990, I started with ELNEC, which was a mini-NEC based program. In 1995, I started EZNEC, and I've been doing it actually for a living ever since. And there's something really important I want to say here in a moment. Let me go ahead and see if I can get my screen up. You don't want to look at me, really. One moment here, please. I'll figure this out. Share screen. I'm sorry, I'm not really super quick at this, so let me see if I can get rid of the icons. I want to bring up my PowerPoint presentation. Please bear with me for just a moment. Okay, good enough. If I did it too quickly, I need to start up my PowerPoint before I turn off my icons. Okay. There we go. Now, can you see this screen? Can somebody please let me know?
We can, Roy, yes.
Okay, good. Okay, good. I've got an awful lot of other stuff on here besides the main screen antenna modeling logo. I assume that nobody else is seeing that. Okay, antenna modeling. And the really important thing that I want to say right off the top here is that I'm going to retire at the end of the year. And I've been doing this, like I said, full-time since 1995, and I've been doing it since 1990. It's time to retire and do other things. And what I'm going to do at that date is I'm going to release EZNEC to the public as a free program, and it'll be my professional program, which normally sells for $525. Plus, it'll have some extra capabilities that even the pro program doesn't currently have. People can be free to buy it now if they want, or they can wait until the end of the year to get it. All the details are here at this link. So please take a look at that before you buy EZNEC or make any decisions about it. Okay, what do the antenna modeling programs do? Well, it doesn't do this. We would like it to, but it doesn't. And what it does is you describe the antenna to the program. EZNEC and most of the similar programs are not antenna design programs. They analyze a design that you make, and it's very helpful in the design of antennas, and it's widely used for designing antennas. But you have to do the initial design, and then you can model it, and then the model will tell you what it does, and you can modify your design to make it do more like you want, and so forth. There actually is an optimizer available that will run EZNEC automatically and do optimization for you. That's Auto EZ, and you can find a link for that on the regular EZNEC webpage. And you describe the antenna to the program as a group of straight wires. You can approximate circles with straight wire segments. You make polygons. You can put in sources, loads, traps, loading coils, and so forth, transmission lines, and ground, sort of ground, and get the results. And it'll tell you the pattern, gain front to back ratio, anything you want to know about it. You can find where the currents are on the antenna and on other objects around the antenna. You can find the source impedances, the SWR, what you want to know about the loads, dissipation, and so forth. It's very good for assessing the interaction with other antennas and conductors. Something to keep in mind is that the program makes no distinction between what you think is an antenna and any other conductor. It just sees a collection of conductors. You put your sources where you want, and in what you probably consider the antenna, and it goes ahead and calculates the whole system without any respect to what you consider the antenna and what you consider to be just a rain gutter, for example. People sometimes ask me, tell me that they've got a small city lot and they've got 4 antennas in the backyard on various bands and so forth. And I explain to them, no, you don't really have 4 antennas in your backyard. What you've got is 1 antenna with 4 feed points, just because of the interaction on the antennas. And you can model just about any kind of antenna that you can describe as a collection of straight wires, and some of them are listed here, just a few of them. They don't have to be any of these classes at all. The things that it does not do very well or can't do at all are slinky antenna, because of the fact that you've got a huge number of turns in the coil. Although the EZNEC Pro program that's going to be free probably would do a slinky antenna pretty well, because you need a huge number of little short wires in order to do it. But it will automatically generate the helix for you, and it'll handle up to 45,000 short wires if you're willing to wait for the calculations to complete. Patch antennas it can't do, or strip line antennas, same thing, because they have a dielectric that is an integral part of the antenna, and the program does not have any way to account for the dielectric. Horns and parabolic reflectors you can do as a wire grid model. Matter of fact, if you look in the background here, the PowerPoint picture of a parabolic reflector, and it looks like a wire grid, and you could do that with EZNEC just fine. The problem is that when you're modeling a parabolic reflector, usually the thing that interests you is the side lobes, the minor side lobes. You want to know how much leakage you have and so forth. And if you're trying to model a solid parabolic reflector with the wire grid, it's not going to show you those details accurately. They'll show you accurately what a wire grid parabolic reflector would do, but not a solid one. Okay, how it does it? Well, we all know that antennas run pretty much by magic, and you need wizards and so forth to do the calculations or actually incantations, but that's not really how it works. There is a little man there behind the curtain, and he is twisting the knobs and so forth to do the calculations, and it's a lot more complex than you would think. The calculations are done using, would you believe, physics and mathematics. And EZNEC uses a program called NEC2 for calculations. That's NEC is for numerical electromagnetics code. And NEC2 was developed in the 1970s. It ran on mainframe computers, was designed to take input from punch cards and produce output on paper, on fan fold paper. And it does a very good job of that. But what I did, what EZNEC is, really is a human interface for that, which reduces it to graphics outputs and a lot of graphical input and an awful lot of other features that NEC doesn't have. At last count, EZNEC, that is just the human interface part of it, consists of more than 70,000 lines of code, every one of which I wrote. And NEC2, which it uses for calculations, is another, I don't know, several tens of thousands of lines of code. So NEC2 does the calculations, EZNEC is an interface for it, but it's built in, NEC is built in, and I've got a special speeded up version. It's very much faster and so forth than the original NEC2. And NEC2 applies the same laws of physics that govern antenna operation, and they're not trivial. Some people ask me questions about whether EZNEC takes this into a consideration, or that into consideration, or what kinds of antennas can you model with it and so forth. And they're kind of, I think, in visualizing something like a whole bunch of 492/F kinds of equations to figure out this kind of antenna or that kind of antenna. But that's not how it works at all. Because it uses the fundamental laws of physics, the same laws that govern the actual antenna operation, the results will be strikingly accurate if the model successfully represents the real antenna. I'll be talking about that in a minute. So I'll explain a little bit about kind of how it works and what it's doing here, but not like that. But I will show you one page out of the NEC2 manual. This is public domain, by the way. NEC2 is public domain. You can download it and run it if you want. And the manual is also available online. Here's one page out of it to give you a general idea of what's going on in there. There are, the manual is a couple inches thick, I guess. And this is just a teeny part, and it's explaining one part of the calculation that's done. So it's not at all trivial. It's extremely complex stuff, but it's very accurate. So a problem, however, we have with modeling is people tend to put poor information into a model, and yet what comes out is regarded as gospel. You see that all the time. Somebody makes just a total wild guess at something for an input to how many cases of COVID are happening worldwide or something, and put it in a computer, crank it around a bit, and the answer comes out to 8 decimal places. And boy, is that accurate? No, it's not accurate. It's really garbage in, garbage out. And so that holds with modeling also, where if you put in if your model does not represent the real antenna, then the results won't represent what the antenna will do. And you got to remember that computers don't do what you want them to do, they do what you tell them to do. So that's another important thing to keep in mind too. They can't read your mind. And antenna analysis programs don't analyze your antenna. They analyze a model of your antenna. And again, if the model of the antenna is exactly like your antenna, then the results will be exactly like your antenna's results. Otherwise, it won't. Okay, a few words about modeling. Here's a good example of what I'm talking about here. Let's suppose we want to know how much current we're going to have in this circuit consisting of a battery and a resistor. We got 1.5 volt battery, we got 3 ohm resistor, we draw a little schematic diagram down there, which is a model, by the way. We calculate I equals V over R equals 1/2 amp. So we think we know what we're doing here. So we actually get a battery and a resistor, and we put them, hook an ammeter in series. And my God, we're at 365 milliamps. We're 27% lower than we calculated, than our model said. And people tend to say, oh, well, that's there's something wrong with the modeling program. Must be Ohm's law is not correct. Well, Ohm's law is correct. The problem is that our model doesn't match the real circuit. Our model had the 1.5 volt battery and 3 ohm resistor. What we've really got instead is a 1.35 volt battery with a 1/2 ohm of internal resistance, and our resistor is actually 3.2 ohms. And that's why we got the 365 milliamps. There's nothing wrong with the model. It's just that the model didn't represent the real circuit. And if we made a model, the second thing here is the model of the real circuit, and that will give an accurate answer. Now, if you can imagine, we have a gigahertz signal generator, and we put a 3 ohm resistor on there with some lengthy wires. We're certainly not going to even get 365 milliamps. We're going to get something really strange, because we now have several circuit elements that are important that aren't in the model. We've got some inductance from the leads, we've got capacitance, and possibly some inductance in the resistor itself. So that's the importance of actually making the model match the antenna or the circuit. And this holds for any kind of modeling, not only antennas and circuits, but weather and anything else. And you won't ever get the right answer if you don't ask the right question. For example, gain, a term is used an awful lot. Gain is really a ratio of 2 numbers. And you say a gain of 3 dB, and that's only half the answer. The answer also requires knowing relative to what. And not only that, but the gain of an antenna is different for every direction, and that's in 3 dimensions. So if you have something like a Yagi antenna on a tower where you can rotate it, it's got a maximum, and you can point that maximum in any direction you want, then it really does make sense to give a single figure for gain, being the gain of the main lobe. But in a lot of other cases, your antenna is fixed, or you're interested, for example, in what the gain is as a function of elevation angle. Your Yagi antenna might have a gain of one gain at one elevation angle and an entirely different gain at a different elevation angle. Takeoff angle is a term that I really hate, and I refused to use it for a long time in my program as an output, because people tend to think that an antenna puts in all of its signal at one elevation angle, which they call the takeoff angle, and don't consider that, no, it really is radiating at all elevation angles, and therefore has different amplitudes, different gains at different angles. Here's an example. This is this slide here was prepared when I gave a talk in Norway on the topic, so it's a little bit off from the UK. But let's see, as I recall, Oregon from Manchester is something like 320 degrees, so it's not very far off. We've got a couple of trees 20 meters apart, 10 meters high, and they're on an east-west line, and we're in Norway, and we want to talk to Oregon. And here are some figures down at the bottom. Halfwave dipole is about 7 meters long, but we can make an extended double ZEP, which is 5/4 of a wavelength, 17.8 meters long, and so it'll fit between the two trees. So let's try it. So first thing, we model it in free space. And I'm going to see if I can actually do this. Hang on just a minute, please. I discovered a really neat feature, and there we are, in PowerPoint just last night when I was fiddling with this. I can make a little laser pointer on here. So I'll put my little laser pointer on there. Okay, so this is the extended double ZEP, is the blue one right here. And the dipole at the same height, actually, well, in this case, we're free space, so we're not talking about any height above ground yet. That's this one right here. So now we'll put in the effective ground, this next slide. Now we're showing the two antennas superimposed above ground, and we're looking at the gain at an elevation angle 6 degrees above the horizon, which is the elevation angle that you would need to do something like a triple bounce to Oregon from the UK. And what's the main difference between this and the previous one is you'll notice instead of having complete nulls down here, the nulls have been filled in a fair amount. But otherwise, the shapes are pretty recognizable and pretty much the same. Again, the extended double ZEP is the blue one and the dipole is the black one. And now they're being modeled at the same height. And if you look at the relative gain at the pattern maximum, which is up here or down here at the bottom, you see the difference. The EZNEC will tell you the difference between the two of 2.72 dB. And however, look at which direction Oregon is. Oregon is up here at 327 degrees. And the difference in gains between the extended double ZEP and the dipole at that angle is 13 dB, and the dipole is the stronger one. So if you put it up this extended double ZEP thinking that you're going to have 2 dB gain over a dipole, well, yes, you do, if the station happens to be pointing in the right direction. However, if it's off to the side like this, the dipole could beat the pants off of it. In fact, if you look, you'll see that the dipole is stronger, clear from this angle, clear around to that angle right there. So you would be better off with the dipole than talking to people over those angles. And you'd only be better off over this angle. And then some of these angles, you get a slight edge by the extended double ZEP. Here's another quick one. I'm just going to go over this one quite quickly. This is a 80 meter inverted V. This is the antenna right here. The purple lines are showing the currents on the wires. The farther away the line is from the wire, the higher the current. So you can see the current's highest near the middle of the antenna, and then it drops off to 0 at the ends. And we got that pattern. We may want to talk to London. And it looks like we've got almost a complete circular pattern here from that. No, sorry. This is the pattern right here. Looks like a dipole. The dashed red lines. and we've got it oriented to favor London. But now we happen to have a Yagi antenna up on a tower sitting over here. There's a 20-meter Yagi, as I recall from my modeling. And what happens when we excite this antenna, you can see the current on this tower is quite high. You can see this magenta line is quite a ways over from the tower line. And so you have quite a bit of current. You have some on the top, but this acts like a top-loaded vertical, really, which is resonant. Now, I chose these things to be a kind of a worst case to illustrate the phenomenon. And what happens to our pattern now is that we've lost about 4 dB or so. The blue line here is the previous pattern. I'm sorry, that I've got to back up a little bit. The blue line is the pattern, and the black line is the pattern with the Yagi. And when I said the pattern was this dashed line, I was incorrect. I'm showing the vertical and horizontal polarizations here. The horizontal polarization is this very dim green line right here. And then it looks like a dipole at right angles. And the vertical polarization is this dashed red line. And the sum of the two is the total field, which is this black circular line right around the edge. So the pattern is circular in shape. My apology for saying that it was the red one. And so it's the blue in this plot, and the black is the pattern with the Yagi there. So EZNEC can, or other modeling programs can tell you whether the antennas are interacting and what the effects are. Also, what I did here is I put a little decoupling stub right on the bottom of this. It's got a capacitor in series with it, and it can be tuned to actually kind of make a little trap here and greatly reduce the current that's showing up on the tower. And that restores the pattern back to normal. So those are some of the kinds of things that you can do with antenna modeling programs. Now, this is a kind of a difficult talk in order to make, and I kind of hesitated actually giving talks on antenna modeling, especially antenna modeling with EZNEC, for quite some time. And the problem is that nowadays, when I first started doing these, I gave a very simple talk, and it essentially was like this, which just told people a little bit about what antenna modeling could do. And I left it at that. And now, many years later, most people have at least heard of EZNEC, and a lot of people have used it. And some are very skilled with it. So the trick is to make a talk that doesn't completely bore those people who are skilled at it. At the same time, I don't want to snow the people who haven't used it a lot. So I'm going to do a couple of examples here, which I hope will be of interest to both groups and people in between. So what I'm going to do now, if you'll bear with me, is I'm going to go back and start up EZNEC and do a couple of examples in real time and tell you a little bit about the program. I'm obviously prejudiced toward EZNEC being its author, and it's been my source of living for 25 years now, 26 years. And so I'm partial to it. Plus, I'm very familiar with it, obviously, having written it and used it. I do some consulting on the side and of course, use EZNEC for that. But EZNEC is by far the most commonly used antenna modeling program today, and probably once it gets free, it will be even more popular. So let me see if I can end that. And going to next. I'm going to start up EZNEC here. If I can find it. Whoops. Uh-oh. No, sorry, guys. I apologize for the fiddling around here. Okay, now get rid of some of this background stuff. Okay, all I got to do is get rid of the zoom window here. Do that. All right. Hopefully what you see now is the EZNEC main window right here. And I'm sometimes asked why you can't maximize this. And the reason is that the language that I chose to write EZNEC in doesn't readily expand all of the controls on that. There are a whole bunch of things on this in this window. Each one of these little buttons here is a different item, a different object. And the grid here is different and so forth. And in order to expand the screen, you would have to also manually tell the program how to expand all of the other stuff. And it was a real hassle. And so I didn't do it. I didn't really see any big need for it. If it's too small for you to see, Windows has the capability of making text larger. Actually, it'll make everything on your screen larger at the same time. And you can use that if you have trouble seeing it. So this screen doesn't change size. This one doesn't. Most of the other windows are sizable. And so this is the main window you see when you start up EZNEC. It may look a little daunting, but this help right here is the manual. If you go help and contents, that's the entire manual. Now, if it's printed out, and you can get a printable option, excuse me, a printable version of it by downloading from the web. If you really have to have a printed manual, it's over 200 pages. The nice thing about the manual that's online here, the integral manual, is that you've got all of these hyperlinks. And so when you're reading along, if you come across something that you don't understand, or you find a word that you don't understand or whatever, a lot of times there's a hyperlink right here, like add row. If you don't know what the add row is, you can just click the hyperlink and it'll tell you what the add row is. Sometimes it'll just be a pop-up like that. Sometimes it'll take you to another section of the manual, but you can always go back to where you were here with the back button. So the manual is very complete. It's also got a very complete index where you can search for any common word in here, any topic. And if you can't find it in the index, you can actually do a search for any word or phrase in the whole manual. So you can find stuff. And my policy on EZNEC has always been that I will answer any question that people have as long as they first make an honest effort to find the answer in the manual. I need to point out, however, that after I retire at the first of the year, I will not provide any support any longer for EZNEC. I'm actually going to retire. Okay, so that's the manual. And in the manual, there's a section called the test drive. And the test drive is a step-by-step tutorial that tells you how to use EZNEC. It has you start out by making a simple dipole, and then you convert it to an inverted V and so forth. And it gets on, as you go on farther, you'll see sections on things like how to use L networks, how to put L networks into your circuit. And then finally, the very last section here tells you how you can make this rooftop, this metal rooftop model. And the program requires you to enter somehow the coordinates, the end coordinates of each wire. And each of these little teeny wires right here, each one of these little things here is a wire. So this is 1, 2, 3, 4, 5, 6 wires all in series. You can imagine how many wires there are in this model. There's a whole mess, but you can do this whole, you can create this whole structure with EZNEC Plus or EZNEC Pro with entering coordinates of only 2 wires. And wires are along an axis, so that makes it even easier. It means the end coordinates on one axis are the same. And so this tutorial, you don't have to go through the whole thing, but go through enough of it to find out how to use EZNEC if you haven't used it before. Now I'm going to show you how EZNEC can be used to, or any other modeling program, can be used to illustrate some of the fundamental principles of antenna operation. What I'm going to do is I'm going to start with a really example files, which is Vert1. This is one of the example files that comes with EZNEC. And I can click view antenna here, and I can see the antenna. It's the little black line here with the number 1 beside it, which is a wire number. And I'm not going to go a lot into the mechanics of using EZNEC because that's explained mostly in the tutorial. But what I'm going to do with this is this is a model of a vertical antenna, and what's important is that it's over a ground that is got some interesting characteristics that aren't really real, but they're good for analyzing antennas. A lot of times it's important to separate things like efficiency, that is your losses in your antenna, as opposed to things that cause radiation to be reduced, and ground losses from the radial system and ground losses from reflections from the ground. These are all factors that affect the antenna radiation overall, but it's often useful to reduce one or more of those to 0 to see what one of these effects is by itself, so you can see which ones are important and what they do. And I've kind of done that here. This is a vertical, and it's really a model of a vertical with a basically infinite ground plane, or I should say a 0 loss ground plane. So you can imagine a ground plane that maybe isn't terribly big diameter, but it's got a whole gazillion bunch of radials. And so the ground loss, the loss from the radial system is 0 in this model. However, it accurately models the reflection loss, the loss from, and the phase change and the amplitude change from reflecting off the ground. So I'm going to run a vertical plot of this. We've got a plot type as elevation angle, as elevation. So we just go far field plot here. And there is the elevation plot of this antenna. And what it tells you is that the radiation is the strongest at an elevation angle of 26 degrees above the horizon. And then it drops off in both higher and lower angles. And this is called a lot of times a takeoff angle. And so this is a takeoff angle of 26 degrees. That doesn't really mean that the signal just takes off at 26 degrees. It just means that it's the strongest at 26 degrees. So I'm going to save this plot for future reference. So I'm going to save trace as vertical. Okay, now there's something else about this, and that is that the shape of this vertical pattern is very strongly influenced by the conductivity of the ground. And so if this is salt water, for example, let's just do a salt water here. We'll go to ground description, and we can right click this guy, go to salt water down here, and run this guy again with the salt water. Oh, look at that. Now let's take the previous trace we just saved. One moment, please. Well,
Roy,
sorry.
sorry to interrupt. I think you might have mistyped the file name when you saved it. I think you might have saved it as VD for Delta RT.
Thank you. Thank you very much. We'll give that a try. And if that doesn't work, I'll just do it again. Okay. Okay. Well, add trace. And I could go and search through this stuff too. If I go V, it'll show me all the stuff that starts with V that I've got in there, which is a bunch. V. Yep, there it is. Good. Thank you very much. There's Vindert. Okay, now we're comparing the vertical plot over common ground with the plot over saltwater. And you can see that the difference between average ground and the saltwater ground is profound. So if you've got a boat, you put a vertical antenna up, you're going to have very good low angle radiation. Of course, if you hit a perfect ground, this comes clear on down to the bottom and you get a strong signal at the horizon with a perfect ground. But with any finite conductivity, you'll find that the signal strength goes to 0 at the horizon. But it gets really, really low if you have a very high conductivity ground. So you got a boat, vertical is the thing to put in. On the other hand, if you don't, you can see that the maximum is quite a bit higher, and the signal is much lower at virtually every angle. You've actually lost some of your radiated power. It ends up warming up the ground, literally. This affects vertical polarization more than horizontal. Vertically polarized signals have a different ground reflection characteristic than horizontally polarized signals. Consequently, you have way more of this effect with the verticals than you do horizontals. Now let's take another antenna here, and okay, I want to say that one. Okay, I'm going to go backyard dipole. This is another one of the example files, and this is one of the antennas that you create in the test drive tutorial also. And this is just a single dipole, and it happens to be at 20 meters. The vertical was at 40 meters, and that can be important because the ground reflection characteristics are going to be different at different frequencies. So we're going to take and change this to a 7 megahertz dipole. And I'm going to tell it to rescale. I change the frequency to 7 megahertz. I tell it to rescale, and that's going to keep the antenna dimensions the same in terms of wavelength. So it's a half wavelength antenna before, and it's going to be a half wavelength antenna now, but at 7 megahertz, okay? And I also want to check here on the ground description. I believe I had average ground for the other, and this particular antenna isn't average ground. It was a little better than average, so I'll go to average ground. So now it's got the same ground as the vertical did. And one other thing I'm going to do is I'm going to change the height and make it a quarter wavelength high. And an easy way to do that is to change the units. When I have units here, I can select meters, millimeters, feet, inches, or wavelengths for the units. And I'm going to choose wavelengths. And then I'm going to take the wires. This is the description of the wire. And I'm going to change the height to, this is Z coordinate, this is X, Y, and Z. You can see the axes here in this view antenna display. So I'm going to change the Z to 0.25 wavelengths. Okay. Okay, now it's a quarter wavelength high. Now I could change units back to anything I want, but I'll just leave it there for right now. And now we'll do a far field plot of this, an elevation plot. Okay, now let's make sure that we've got our elevation plot in the direction of the broadside to the dipole and not off the end. So the way I'm going to do that is I'm going to go back to the view antenna display and tell it to show the pattern, right? The 2D pattern. We'll show it on there. Okay, there's the 2D pattern being shown on the plot. And you can see that we are looking at the broadside pattern of the antenna. So we'll go back to the 2D plot. Okay, now look at the takeoff angle of this guy. If you want to talk takeoff angles, the takeoff angle is straight up. Actually, it says 84 degrees. Let's see, at 5.74 dBi, and right straight up is 5.73. So it actually is a teeny itty bitty stronger, just a couple of degrees off of straight up. But you can see that this is a cloud warmer. It's radiating almost straight up. It's got a lousy takeoff angle. So the question is, which antenna would be better for DX, for getting those low angles? And it sure looked like the vertical with the low takeoff angle would be the one. But let's superimpose the vertical trace, good old VDRT. And this will put on the same plot with the same scale. Now look at that. Yes, this has got a higher takeoff angle, but for every angle above 14 degrees or thereabouts, let's see, there's 1 dB. If I, let me do one other thing. If I go right here, I can get a comparison between the two. Down here at the bottom, this dB trace, dB primary trace, shows us a difference between the two. And I can move the cursor around and find what it is at any angle. So it looks like down here, about 0.16 dB different there. And that's about it. So that's 13 degrees. So it's at about 13 degrees, they're equal. And above that, the dipole beats the vertical, and at many angles, it beats the living pants off of it. Let's see about the real low angles here where the vertical is actually better, like right there. There's about a 2.3 dB difference at 7 degrees. So at these angles, the vertical is slightly better. Well, that could be a significant amount, 2.6, 2.7 dB at these very low angles. But as you can see, at moderate angles and higher, even the quarter wavelength dipole is considerably better. Now, out of curiosity, let's raise the dipole up to a half wavelength, say, and see how that does. So what we'll do here now is we'll just go to wires. And this time I'm going to not bother entering the new Z coordinates. I'm going to go do one of the many things you can do with EZNEC here. I'll tell it to change the height by 0.25 wavelengths. And presto, we've got new coordinates of a half wavelength. So it's up at a half wavelength now. Okay, now let's run the plot. And now we have a takeoff angle of 27 degrees, which is pretty close to what the vertical was. And we'll add the vertical trace again. Now, which antenna are you going to put up in your backyard? If you can get it up a half wavelength, you get the dipole. And even at a quarter wavelength, your dipole may be a lot better if you're, like I've got a friend in San Francisco that I have a weekly sked with. It's about the only operating I really do except field day. And it's about 600 miles to San Francisco, which is about 1,000 kilometers. And the angle for talking to him is around 30 degrees. And so the dipole, even at a quarter wavelength, beats the pants off a vertical for that path. And at a half wavelength, it's a real killer. And I've got a dipole, 40-meter dipole up at about 80 feet. I got an 80-meter dipole up around 90 to 100 feet. I put that up in my big trees in my backyard with a drone. I put a weight on the drone and attach it to a fishing line and send the drone up. And then by moving the camera, it pulls out a pin that drops the weight. And it took me a while to get the bugs out of that system, but it works pretty well. And I've got some antennas up really high now. Anyway, so there is an example of how you can see a couple of fundamental things about antennas with EZNEC or other modeling programs. Okay. Now I mentioned that it's often useful to separate phenomena. And one thing I'll talk very quickly about is efficiency. Efficiency is the fraction of the power that's applied to an antenna that actually gets radiated. And if you put 100 watts into an antenna, 100 watts comes out. It has to. That's the law of conservation of energy. You can't violate that. So that means if you put 100 watts into an antenna the size of a toothpick or a 30-element beam up 500 feet, 100 watts comes out of each one. Now, in the case of the short antenna, almost all of that power coming out of that is in the form of heat. In the case of the big beam, hopefully it's very little of its heat and it's almost all radiated. But the 100 watts does come out. And a lot of people make the mistake of thinking, well, the reason that the short antenna doesn't radiate well is because it's short, and somehow a short antenna just can't radiate well enough. Well, let's test that and see what the deal is here. So another example file is dipole 1. This is a half wavelength dipole. It's just about as simple as you can get. Half wavelength dipole in free space and at a frequency of about 300 megahertz, where the wavelength is 1 meter. And it's got just all of the classic characteristics of a dipole. If you look at the source impedance, it's actually 82 ohms, and it's got a little reactance. And that's to be expected from a half wavelength dipole. A half wavelength dipole is not quite resonant. And also the impedance is not exactly 73 degrees. You'll get a different impedance depending on the diameter of the wire. And in order to be resonant, the antenna has to be a little shorter than half wavelength. And the amount it has to be shorter depends on the diameter. You can fiddle with EZNEC and discover all of this stuff and verify it. But here it is. The pattern doesn't change hardly at all, however, as you change the length a little bit. So here's your classic, the gain is just about what you'd expect, 2.16 dBi. So what we'll do is we'll save this one, and we'll try to type a little more carefully this time. Dipole. Okay, so now we got the plot of a dipole. Now let's take this dipole here. And right now, since I said that it's a wavelength of 1 meter, so the length of the dipole you can see is this dipole extends from minus 0.25 meters to plus 0.25 meters, so it's exactly half wavelength long. Let's go to 0.01 wavelength long, say. So we'll go minus 0.005 to plus 0.005. Okay. It just disappeared on us. If we reset the size and everything, it'll show back up again. It's really hard to see. It's a red wire because it's selected against the red axes, but it's there. Okay, so now it's 0.00, it's 0.01, 1/100th of a wavelength long. What kind of gain would you expect this now to have? Now, I have to point out that there is no loss in this model. And so it's not terribly realistic, but there's no resistance in the wire, which is really the only source of loss possible in this kind of a model with only this one wire. You have to start thinking about it. Let's see now. Let's suppose we have a 100% efficient antenna. We're talking about the gain in terms of an isotropic. An isotropic antenna radiates all of its power exactly equally in all directions. And in order to conserve energy, we have to realize that if we want to have any gain larger than that, this spherical pattern will have to bulge out somewhere. And if it bulges out somewhere, it's got to bulge in somewhere. So we can't make an efficient antenna. It won't be possible to make an efficient antenna with a gain of less than 0 dBi, because if it had less gain, it would be poking in somewhere, then it's got to be poking out beyond 0 dBi some. I hope you're following that. I really should have some graphics to illustrate that, but I don't. So I'm saying that if an antenna is 100% efficient, no loss, then the smallest possible gain it could have is 0 dBi, and that would be a perfectly circular pattern in all directions. So let's see what kind of gain and pattern this thing has. Okay, looks pretty much like the half wavelength dipole, doesn't it? Let's take and add our dipole trace to it for the half wavelength dipole. Now we have the half wavelength dipole is the blue trace, and the 1/100th of a wavelength dipole is the black trace. And by choosing this, I can actually look at the gain difference, which is about 0.4 of a dB. And the only reason that there's that much difference is that you'll notice that the 1/100th of a wavelength dipole pattern is just a little bit fatter. It extends out this way a little bit, and therefore it was in just a little bit here. Otherwise, they're virtually identical. So the fact that a short antenna does not, in real life, in your experience, radiate as effectively as a long antenna isn't something to do with its ability to radiate. By the way, the reason that the patterns are different at all is the current distribution on the antenna. The current distribution on a half wavelength antenna is pretty sinusoidal. It looks like a sine wave, and this antenna is more linear. You see how it drops off there? Actually, it looks a little bit exponential. So but it doesn't have the classic shape of the longer dipole, which is a piece of a sine wave. And that's why the pattern is different at all, is because of the different current distribution. So why are short antennas not as, why don't they do as well as long antennas? Well, the reason is they're not as efficient. And the reason they're not as efficient isn't anything to do with the radiation characteristics. It's just the fact that in order to get that kind of field radiating from such a short antenna, you've got to have humongous currents flowing in it. I don't have the graphics right here, but it takes something like 600 amps or something to radiate 100 watts. And so your I squared R losses eat you alive. Also, you have, if you look at the source impedance of this guy, you'll see you've got 5,000 ohms of reactance, and you have your resistance is 0.01706 ohms. So you need to somehow match that to 50 ohms or some reasonable value in order to get some power to go into it. And in order to do that, you're going to need a lot of inductance, and inductors are lossy. You've got copper wire, and that amount of inductance would require a lot of wire, which is going to have a lot of current going through it also. So that's where you get an awful lot of loss, and consequently, once you match the thing, you will find that very little of the power actually gets radiated. So I think I'm running down about 15 minutes left here, so I think I'll devote the rest of the time here to answering questions. I do have a little bit of a summary, which I will try to bring up here quickly. And if I go to somewhere around, what do you know? Some days you're lucky. I want to emphasize that you get very accurate results of the performance of your model antenna. And if your model antenna isn't like the real antenna, then your results won't be like the real results. And it's up to you to tell the program what your antenna is like. I had an Australian fellow years ago that kept emailing me that the resonant frequency of his loop antenna was off, or his quad, it was off. And he'd tried everything and he just could not get it to agree with the model. The model just didn't agree with it. And he was sure that there was some kind of a bug in the program. And I kept telling him, look for some difference between your model and your real antenna. And of course, this was after I also explained to him how difficult it was to really make good measurements. And very often the problem is in the measurement. So anyway, this went on for a while and he finally gave up. And then something like a couple of years later, he emailed me. He said, oh, I found it. He said, I had these little things in the corners of the antennas, the little spreader thingies or clamps or something. And I put those in the model and now it agrees. So that kind of stuff happens all the time. And there are some antennas that you can't accurately represent with a model, and I showed some of those up front, and some cannot. And always check and see if the answer makes sense. That's true for any kind of modeling. There is my website, my email address, and please, again, anybody who has any interest in buying or waiting for the free EZNEC, go and see that that page at my website. So that is it for my presentation, except I can take a few questions.
Roy, thank you so much for your presentation, which has been fascinating. And I think, first of all, I'd want to just round up a number of contributions that have come through chat and also questions to express heartfelt thanks for all of your work on antenna modelling and also your contributions to magazines over the years. And there have been a number of wishes, best wishes for your retirement. So I hope I've wrapped up those from the chat and done those justice to the various contributors.
I have to say, I am very, very thankful to all of my customers over these years because I regard myself as an escapee from the Dilbert cartoon. I was working for a large company, Tektronix, for years, and it became the very image of the big corporate company, and I was able to escape and be a one-person company for all of these years, and it's been wonderful, and it is thanks to all of you folks. Thank you.
Well, people clearly want your software to live on, Roy. There was a question earlier which I took the liberty of answering from Dave N2OA and pointed him to your website on why you couldn't release the source code. But
I may reconsider and
well,
release it.
Kyle Hussman has an observation to thank you for your work, and wonders whether if a volunteer offered to shield you from all of the questions, whether your work could be archived as an inspiration for future generations. So we'll copy that and forward that to you separately. I think that's the best way of dealing with that one. And then there are a couple of practical questions. One from John Mace. What is the best way of simulating buried radials in mediocre ground? And then Darren M7ENP, how would you model a trap on, say, an inverted L?
Okay, first of all, the ground. Ground is really the weak point of this and other modeling programs because it assumes that ground is homogeneous to an infinite depth, and real ground is not. And there's a lot of times there's no ground conductivities and so forth that you can enter in that really imitate the stratified ground that you really have. But to the extent that you can, with the NEC-based programs, the best you can do to simulate radials is to model radials just very slightly above the ground. And that'll get you fairly close. It won't be tremendously accurate, but it's the best you can do because NEC2 does not allow buried radials. There is an NEC4 program that will, and I do have a version of the program that does incorporate that, but it requires you to get an NEC4 license. And after I retire, there will be no way for me to assure that. However, the program I'm going to release free will be able to run an external NEC4 program. So if you want to bungle up the $300 or so, well, it's for the US and it's more for overseas. The license for NEC4, the free version will be able to run an NEC4 program externally, and that will allow you to directly model buried radials. Okay, so that's the first one.
Thank you.
And the trap, and by the way, that is discussed in the EZNEC manual. If you look under ground, about ground, it is explained in the EZNEC manual how to model those. Trap, there is an actual trap model included in the loads, the load types, which consists of a series RL with a capacitor across the whole thing. And that R simulates the resistance of the inductor in the trap and a capacitor across it. That's one way to model a trap. That works okay if the trap is physically short and doesn't take up much of a wavelength. If it does, then what you've got to do is model the trap as a helix with wires, and it will, EZNEC will create a helix for you. It's got an automatic helix creation feature, and that will give you a better model. You can put a model a helix with wire, put resistance in the wire, and put a capacitor load across it.
Okay, thank you. A number of other questions have come in, and I'm just scanning them to try and consolidate one or two. A question from Alan G8UHN. Is it possible to model a GPR antenna?
What's a GPR?
He doesn't specify. If Alan wants to come back with some more detail, we'll see.
Yeah, I get queries like this quite often. Can you model a G5XP antenna or people love TLAs, that is 3-letter acronyms. So can you model an XPG antenna? And so then I have to go to the internet, look up and see what the heck is an XPG antenna. So.
And I'm afraid you're paying the price for an inexperienced chair. It may be a UK abbreviation that everybody else knows, and they're sitting there laughing. But we'll see if Alan can come back with something.
Okay.
And then question from Michael VE1LEB. You showed an example of a rooftop. Does the conductivity of the roof material make a difference in the results?
It can. It certainly depends. If your antenna is right down close to the roof and horizontal to it, it probably will. If the antenna is not, doesn't have those characteristics, it may not. But you can insert loads into the wires in order to simulate resistance of some other material than metal. That model was intended to model a metal roof, and a metal roof, probably the conductivity would be insignificant. Any amount of practical resistance a metal roof would probably be insignificant. If you want to model something else, if you want to try to model concrete or something that's partially conductive, you can, in theory, enter loads into the model to simulate the resistance. However, I don't know of any possible way to figure out what those load values would be.
Okay. And somebody's told me what GPR means. It means ground penetrating radar.
Oh, okay. So what was the question again, please? The whole question?
Is it possible to model a ground penetrating radar antenna?
I don't know. I don't know what kinds of antennas they would use for that.
Right.
So I'm sorry.
Okay, that's fine. Someone's asked whether capacitors can be added between wire sections.
Oh, certainly. Certainly, there's a thing called a load, and it could be a capacitor, a resistor, an inductor, a series RLC, a parallel RLC, or this trap model that I discussed.
Right. Okay. Thank you. Mike G0JXX. What led you to develop the modeling software?
Well, many years ago, and this would have been well before 1990, it's probably in the middle 80s, somebody gave me a CD which had on it a program called EZNEC. And it was written in GW Basic. Some of you may or may not remember that. And it was written by some guys down at the Naval Ocean Systems Center in San Diego. It's public domain. And what it was a program that uses the same kind of approach that NEC2 does, but it was designed to be able to be run on the PCs of the day, which were back then the XT and the AT type computers, just a kind of a couple of steps up from the original IBM PC. And so one day I'd been working an awful lot on understanding phased arrays and so forth. I got a collection of paper. I spent a lot of time in the IEEE library. And so I got out this program one day, dusted it off and tried it. And I was just absolutely gobsmacked by what the power of the thing. I've got, you have to understand that before these modeling programs, just calculating the feed point impedance of a dipole there were like 5 complicated approximation methods to try to figure it out. And some of them worked well with long dipoles, some worked better with short dipoles, some worked better with thin dipoles, and so forth. And even modeling that was an approximation and not a very good one. And then modeling 2 antennas, the interaction between 2 parallel antennas was very complicated, but if they were cocked relative to each other, it was almost impossible to do. So I all of a sudden saw that, gee, here's something that can do all of that, but it was user hostile. So I started hacking at it, and I decided, gee, you know, like if you wanted to change anything, you had to start all over again and enter everything. And the only way you could describe the antenna was by entering the wire end coordinates of every wire and so forth. So I spent quite a bit of time hacking on it just in my spare time until I had something I considered to be usable. And of course, the computer could just barely run it back in those days. And I really wanted a faster computer, but I didn't have any way to justify spending another couple $1,000s, which was a lot of loot back then. And I saw that a fellow named Brian Beasley was selling a mini-NIC based program for about $100. And so I thought, well, if he can sell his, then I can sell it, and maybe I can make enough money to buy myself a new computer. So I sold EZNEC for $49, and the rest is history. It was, I think, 3 months later, I had my new computer, and then about 5 years later, I quit my day job and did it full time. So that's the story.
Wonderful. Well, it brings us to 1729. I think we're finishing on time, which is great in what we've been asked to do. And I think I just want to reiterate, Roy, we'll try and get a copy of the chat and the questions to you, because there are many expressions of good wishes for your retirement, and many thanks for everything you've contributed over the years. So thank you very much, Roy, for a fantastic presentation.
Well, thank you very much. My pleasure. Good seeing all you guys again. I hope to see you in person before long again.
Bye.